Hi, my name is Uli. I'm a student at Aviv University, and today I'm going to talk about comparison graphs, a unified method for uniformity testing. So what is property testing? Basically, we have some large object that we wish to test, and this object can be a graph or a distribution, maybe a function. We want to test for some properties, so we're not able to see the entire object because it is so large, but we can maybe ask if a graph is bipartite or whether a function is monotone or very far from that. And the complexity measure is the bits of information that we're allowed to see, so the samples that we get from this very large object. And once we get our samples, and this is a randomized process, we're trying to answer whether we have a property or we're far from that with a high constant probability. So in this talk, we're going to focus on distribution testing and specifically the problem of uniformity testing. And in the problem of uniformity testing, we're exposed to samples from a distribution that is over a domain of size n, and we need to distinguish the two cases. Well, the yes instance would be the specific uniform distribution over the entire domain, over all n elements, and the no instances would be every distribution that is epsilon far from uniform. And by epsilon far, I mean in L1 distance, or otherwise statistical distance, total variation distance, these are all the same, up to a constant factor. And this problem in the standard model was solved long time ago, so let me give you some broader background about that. So uniformity testing was first introduced in Fox 2000 in a paper by Fortnow, Rubinfeld, Smith, and White. But it was also implicitly used in a Kohlrach and Ron in 2000. And the method used is the collision-based tester. And their analysis showed that square root of n over epsilon to the fourth is actually enough samples to perform uniformity testing. But even for the easiest case where epsilon is large, where epsilon is a constant, the birthday paradox shows that you cannot perform uniformity testing unless you have at least square root of n, order of square root of n samples. So the dependency of n is quite clear right on the beginning, but the dependency on epsilon, the proximity parameter, kind of made a mystery, and it stayed a mystery for roughly 10 years, until a paper by Poninsky in 2008 showed a lower bound of square root of n over epsilon squared, and a matching upper bound, but not for every value of epsilon, rather only for large enough values of epsilon. And the paper 6 years later by Chen, Diakonikolas, Valiant, and Valiant also used a different method, a different tester, to show that this is indeed the right sample complexity for the entire range of possible values for epsilon. Another paper that I would like to mention is a paper by Diakonikolas, Goulikis, Peebles, and Price from 2016 that actually shows that the original tester, the collision-based tester, is optimal. So using square root of n over epsilon squared samples and performing the collision-based tester would work. Okay, so what is exactly the collision-based tester? Well, it relies upon the notion of collision probability. And collision probability of a distribution is basically the chance of two independent samples from said distribution to have the same value. Or alternatively, this is the L2 norm squared of the distribution. And two simple facts about this notion of collision probability is this. Well, if we consider all the distributions over a domain of size n, then the one to minimize the probability of seeing collisions is a uniform distribution. And this is quite known and trivial, but a tiny bit less trivial fact is that this is quite robust. So any distribution that is epsilon far from being uniform, where again we're epsilon far in L1 distance, it has this condensed mass over few elements that would cause more collisions. It has a noticeably larger collision probability. That's being said, at least 1 plus epsilon squared over n, which is a noticeable gap from the collision probability of the uniform distribution. So our strategy would be to estimate this probability, the collision probability of the distribution that we get samples from. And once we do that, well, we can, if we have a good approximation, a good estimation of the collision probability, we can compare it to some threshold, and if it's small enough, then we'll say it's uniform, and if it's large enough, then we'll probably get samples from a non-uniform distribution. So a very naive estimation would go just by definition and would say, okay, what happens if I draw two samples and compare them? Well, then I can observe the indicator of whether they had the same value or not, and this indicator is either 0 or 1, which is kind of useless. But what's good about this indicator is that in expectation, this is going to be exactly the collision probability. So what we need to do is to make more comparisons and average over many such indicators. And indeed, this is what Goldreich and Braun were doing. And in order to maximize the amount of comparisons with minimal samples, you would want to compare basically every possible pair. Let me just point out that we do create some dependencies which might interfere in the future. For example, we can see that S1 is compared both with S3 and S2, so the indicator of this comparison and the indicator of the other comparison are not independent. So some dependencies are created, and this is actually the reason that the optimal analysis took so long to achieve. So the tester is this: draw Q samples, compare all possible pairs, and normalize by the number of pairs. So count the collision, normalize by the number of comparisons that you've made, and this is a good estimation for the collision probability, as long as Q is large enough. Okay, so let me jump back to the present, to some recent line of work about distribution testing. And this line of work considers distribution testing under constraints or in various models, and not necessarily the standard classic models that we're used to. And let me just quickly go over some models that are considered lately. So one model would be a multi-party interactive model, where we have many players and each one of them gets either a single sample or maybe several samples from the distribution, and they can interact with one another, and they somehow collectively need to output a decision about whether the underlying distribution has some property or not. And another model would be a simultaneous model, where the players cannot interact, but each of them has its own samples and its own decision or idea of the answer. It can only send a short message or a signal to some referee, and the referee collects all the signals from all the players, and it needs to output, again, whether the underlying distribution has a property or is very far from having it. Another model being considered is a streaming model, and we're going to get into that one later on. But basically, the samples now arrive as a stream, and we cannot store all the samples all together, but we need to store only some of them. And while processing the entire stream, by the end of it, we want to decide whether we have the property or not. And I kept on saying deciding whether we have the property, but usually, I think like 80% of these papers concern with uniformity testing. And this is not only because this is the most fundamental problem in distribution testing, but also there's a good reason for that. This is also a very useful problem. So here's some reasoning for that, some evidence. So say we get samples from an unknown distribution. Well, the optimal goal would be to learn the distribution. But even if I want to learn the distribution, or if I want to output a distribution that is somewhat close to the real distribution, this would take order of the domain size, linear number of samples in the domain size, which is quite a lot, because we know that for uniformity testing, we only need the square root of the domain size. And here's a better idea. Well, maybe I'll start by having some distribution in mind, not necessarily the uniform distribution, but some distribution. And now I only wish to test whether the samples come from this exact distribution that I had in mind or something that is very far off. And this task is called identity testing. It's much faster than actually learning the distribution, and therefore it is very useful. And the work by Nicholas and Ken from 2016 actually showed that identity testing can be reduced to uniformity testing. And a modified reduction made by Godlife later that year is actually so black box that you can use it in any known model where distribution testing is being considered. So basically, for each one of these models, not only we solve uniformity testing, or we have some testers that can test for uniformity, but we also get identity testers for all of these models. So let me try and give you some motivation. So our motivation is going to be the following. Maybe not only we can solve all these identity testing tasks using uniformity testing specifically, but maybe we can also solve uniformity testing and therefore all identity testing problems in a generic way that would fit many different models. And of course, we don't presume to include all models. Some models might be very peculiar, but maybe a lot of models can be captured using the same perspective. And indeed, one candidate for that is the collision-based tester, because ideas of the sort, something like approximate the collision probability, arise in more than one model in the last couple of years. And of course, the main obstacle is that if we reduce ourselves to the original collision-based tester, well, it tries to compare all the pairs. And this is obviously impossible in any constraint that you can think of. So we need to adjust it. We need to somehow generalize the notion of collision-based testing. And we do this using the definition of comparison graph. So what are comparison graphs? Well, this is a new perspective of how we view our samples and which samples we choose to compare. So the set of nodes in a comparison graph actually has a sample on each node, sitting on each node, and the set of edges is a pairs of nodes, pairs of samples that we're willing to compare. And different set of comparisons would create different set of dependencies, you know? And using this, we can induce a generalized notion of a collision-based tester, where each graph induces a specific instance of a collision-based tester, and it does in the following way. Well, the edges merely indicate where do we want to look for collisions. So for each edge of G, we have the indicator of whether it has a collision on the two sides of it or not. And the estimation for the collision probability, what the tester, the algorithm will do is basically try to approximate using only the comparisons that are indicated, that are dictated by the graph G. So only summing collision indicators over the edges of the graph G, and of course normalizing by the number of edges. And as usual, well, if we got a low estimation, we would say uniform. And a high estimation, we would say this is far from uniform. This is business as usual. Okay, so let's try and go over some examples to see the duality between algorithms and the graphs that induce those algorithms. So the original version, the original algorithm, basically take a bunch of samples and compare all possible pairs. And this is, of course, the click graph, right? Because we take every pair of samples and compare them. Well, let's see what a different graph would be. So let's say star graph, the first graph that came to mind. And this also induces some tester. And one way to define this tester is maybe, okay, we take the first sample, we put it in the middle, and we compare every other single sample with that one. So I don't know what this would give us. It's probably not a good estimator for the collision probability. However, a different algorithm that we have in mind actually proves itself to be quite useful. This is the following. So maybe we have a large set of samples, maybe even more samples that we would need in the classical model, but it would be much easier to divide them into small batches and only compare within those batches. So the comparisons are somewhat, in a sense, more local, you know. So we take this large amount of samples or nodes that we have, and we divide them into disjoint cliques. And within each batch, we have a full clique because we compare all the pairs within this batch. Just a small note: while this graph is somewhat comparable to the first graph, where we have one huge clique, well, if we would want to have the same amount of comparisons, not nodes, but comparisons, edges, then of course we would need more nodes to achieve that when we need to have many different cliques. But on the other side, when we take small batches, when we take many different cliques, apparently we would create far less dependencies than we would have in the original tester. So this is something to keep in mind, and it can be illustrated by taking an extremal case. Well, if we divide ourselves to batches of size 2, this is basically taking a graph which is a perfect matching. Well, the resulting algorithm is, okay, draw a new, fresh pair of samples for each comparison that you make. So now each collision indicator, each comparison that we make is completely independent from all the other ones that we use. So here we drop the dependencies to virtually none. Oh, how can we use this new perspective, this new definition of comparison graph? Well, let me take you back to 2016. This is the analysis of the original tester. We're not going to go into any technical details at all, but this is data that we now label as a clique graph. And we know that by counting collision, normalizing by the number of comparisons, we know that this is a value that in expectation should be close to, should be exactly the collision probability, but we want it to be close, and for this we need some concentration measure. And indeed what they show is what one would show, that whenever the number of samples is at least square root of n over epsilon squared, this is called the number, then the variance gets low enough. But in actuality, a closer look shows that the variance consists of two different terms, and one of them actually gets smaller merely because we have enough indicators, we make enough comparisons in our algorithm, while the second one drops because we don't create too many dependencies. And this is quite abstract, but actually we can quantify these dependencies, and we played with that before. So a dependency would be quantified by two comparisons, a pair of comparisons that share a sample. So anytime we have this image inside our comparison graph, this two path, this is a dependency right there. Okay, so now we can get a structural result over the notion of comparison graphs. And it goes as follows: whenever a comparison graph fulfills two conditions, then it is guaranteed to induce a good uniformity tester. So first, let me just remind you, a good n-epsilon uniformity tester means that with high constant probability, we can distinguish the case that the underlying distribution is uniform from the case that the underlying distribution is epsilon far from uniform, say in L1 distance. And the two conditions that the graph needs to hold is, as we said before, well, one is that it makes enough comparisons, so the number of edges is large as a function of n and epsilon. And two is that it has relatively few dependencies. And as we just said, well, dependencies are quantified by two paths. So we define CG to be the number of two paths in the graph G, and this should be this ratio of CG as to the total number of pairs of comparisons, not pairs of samples, but now it's pairs of comparison. Well, this ratio should be small enough. Okay, so the details doesn't really matter much, but let's just see how this generalizes the previous result, the previous analysis in 2016. Well, the previous analysis was correct specifically for the graph of this structure, that is clique over Q samples. But for this structure, we know that the number of nodes, the number of samples is Q, the number of comparisons is exactly our order of Q squared, and the number of dependencies created is of order Q to the third. And having these values in mind, so we know that this single condition, this one condition that the number of samples is more than squared over epsilon squared, you know, this is called the number again and again. Then this an easy calculation that I'm not going to go over shows that both condition 1 and condition 2 actually hold for a clique of t size q, and this immediately guarantees us that this is a good uniformity tester. So good, our theorem actually generalizes the previous analysis. So the last part of our talk, I want to get to the punchline and show you some application and another short disclaimer where here again we're going to ignore constant suppose text. So let's see what is the generic recipe that we use in order to leverage the previous result and devise a tester in a new model. So we have the tester requirement. These are known to all. We need the uniform distribution to be accepted with high probability and any far distribution to be rejected with high probability. This is not going to change for different models. However, with different models, we might have a different complexity measure. Probably would be related to the number of samples, but not necessarily. And we also would have the model constraints, and this is the interesting part. And the main idea is, well, let's translate all of this to graph notation. Let them speak in the same language. And, well, the first part we've already seen. We did have the structural theorem, theorem 1, that said, okay, if we have certain type of graphs, then we're guaranteed they are guaranteed to induce a working uniformity tester. This is good, but with those other parts that concern with the model, well, we have to use some heuristics, obviously. For each model, we'd have to use some other heuristics, and hopefully we're going to get something interesting. But once we've done that and we got everything in line with graph constraints and graph measure, then the problem becomes kind of straightforward, not necessarily easy, usually is, but definitely straightforward. Well, we simply want to optimize some graph measure, and we can only choose graph that answers the constraints of the model and the constraints of the tester requirement in order to actually induce a uniformity tester. And all we are left is choosing the right graph. So this is, I think, the core idea of the paper. Let's see one way to realize that, and we're going to do that in the streaming model. So we're going to talk about the streaming model in the next couple of minutes. And in the streaming model, the problem of uniformity testing was first introduced a year and a half ago, 2019, by Diakonikolas, Goulikis, Ken, and Rao. And I think the wishful thinking of their algorithm is somewhat the following. So we have a long stream of samples, but we can only store m samples at a time. The idea is, why not? Let's store the first m samples and use some sort of collision-based testing to try and compare these with all the rest of the samples. So upon receiving another sample and another sample, we simply compare them with those samples, this first batch that we put in our memory. And for each sample, we do that. And we also need to maintain in the memory some global collision counter, but trust me, this is not very hard. It takes very little space. And when we're done with that, and hopefully we've taken enough samples and we have done enough comparisons, then we can do some sort of collision-based test. So we can estimate the collision probability and then answer whether we're uniform or not. This is the idea in principle, but the execution is not quite as easy as it sounds like it should be. And the actual tester, well, it has some adjustment. It does do a bit more than just counting collisions. And this modification, this adjustment, these added procedures actually affect the analysis quite heavily. So the analysis is not as straightforward as you think. And after doing some fine work, they do end up obtaining a tester, but it doesn't work for every parameter. So it does have a limited range. So this analysis comes with a cost. So it's great analysis and it shows very good sample complexity when it works, but it doesn't work for every parameter, every value of the parameter, memory parameter M. However, they do show that in certain range of M, not only that it works and it gives a good tester, but they show a tight lower bound. So this is an optimal tester. This is definitely a way to go, but somewhat it still seems a bit off, and maybe a way to understand it is through the comparison graph perspective. So I have to say that they did call this tester a bipartite collision tester, because obviously we compared the first batch of samples M with the entire second batch of samples M prime, and they knew what they were doing. But still, just let me put it right on your face. So this is the comparison graph that we're trying to use. This is the comparison graph that supposedly induces the tester. We said this tester does a bit more than just counting collision, but it's presumed to be the tester induced by this comparison graph. And their analysis also gives this the same conditions that we got on our in our structural theorem, that the number of comparisons, well, for them it's specifically for any bipartite comparison graph, but still the number of comparisons must be at least n over epsilon to the fourth. And since we assume that M prime is the larger portion of the stream, so the sample complexity is basically M prime, which is n over m epsilon to the fourth, and this is probably the optimal sample complexity for this problem, whenever it's possible to obtain that. Note that, well, I've written the conditions of our structural theorem here on the right side. Note that the first condition, they got the same condition in their analysis, but for the second condition, well, we cannot hope to fulfill it. We cannot hope to apply our structural theorem, because this type of graph, the bipartite complete graph, it just has too many dependencies, especially when M is rather small. So we have these edges, these vertices, samples with very, very high degree. So we said that dependencies are quantified by the number of two-path, and in a complete bipartite graph, we had a lot of them. And we cannot even hope to apply our theorem. So what exactly went wrong, or is there anything that went wrong? And what I think is the right perspective is that this graph actually admits too many dependencies. Maybe they are unnecessary, and this is also the reason why the previous results were a bit rocky. You know, they needed to use heavy analysis, and they needed to adjust the algorithm a little bit, and probably because the dependencies here were very problematic. So maybe we can ditch those dependencies. Maybe we can use a different graph. Is that not the right graph for the streaming model? And this brings us to the question, what is the right graph, and how do we choose a graph for the streaming model? This is a good question, and here's a partial answer. We do obtain a nice lemma about the streaming model that states the following. If a tester, a collision-based tester that is induced by some comparison graph G, can be simulated in the streaming model with memory of at most m samples, then it means that the average degree of G cannot be too high. It cannot be larger than 2 times m. So the maximal degree can be high, because we can take the first sample, as they do in the other tester. We can take the first sample and compare it basically to the rest of the stream, and it will have a very high degree, but the average degree cannot be too high. And this holds true for the complete bipartite graph, but it holds true for other graphs that seems maybe more pleasant. They don't have as many dependencies as the bipartite graph, and they might be a better candidates for collision-based testing in the streaming model. So what was the problem? The problem was that we kept those same samples for a long time, and they ended up gaining many dependencies because we compared them to many different samples. And the idea, and it's encapsulated in this graph, the idea is, okay, let's get rid of all the sample. Every time we process a new sample, not only we compare it with all the samples that we have in our memory, but we also we take the oldest sample in the memory and we replace it with the newest one. This means that any sample, upon being processed, is compared to the last m-1 samples that have been processed before it, and it's going to stick in our memory for another m-1 step, so it's going to be compared to the next m-1 samples, so its degree is going to be almost 2 times m. This is almost optimal with this restriction that we have by the model constraints. And this is a nice graph, and we can analyze this graph, but there is an even simpler graph that we can analyze, and probably or provably without losing more than a constant factor in our complexity measure, the number of samples. And if we give up a bunch of comparisons, that maybe we can just divide and conquer, maybe we can make the following. Each time we take a batch of m samples and we compare them only among themselves, so this is essentially a click, and then we just get rid of them and take the new batch and again make comparison only within this batch and throw them out, and so on and so forth. All in the meanwhile, of course, just as before, we said that it cost us very little memory space to keep track on the global collision counter. So let me just sum up, because this is the true graph, this is the correct graph to choose for this model. And to sum up, this would be a little bit like that when we squeeze it into the generic recipe. Well, the tester requirements stands for theorem 1, and we know how they look like. But specifically for the streaming model, well, we have this heuristic and we have this streaming lemma that said, okay, if we can only store m samples at a time, this means that the average degree is at most 2 times m. And this is what our graph must fulfill. And the samples in the entire stream, this is the complexity measure, the number of samples that we see in the entire stream, and this is simply the number of nodes in the graph. And as we said before, so this easily leads us to a nice structure of a graph that fulfills all these requirements, and the graph is k-disjoint clicks of size m. And well, I'm going to skip this small calculation in the cloud, but essentially it's very easy to calculate and see that the total number of samples in this model, for this comparison graph or this algorithm, is still n over m times epsilon to the 4th, which means this is the optimal sample complexity, the same sample complexity obtained by the bipartite collision tester, only now this can be obtained for any parameter m, as long as we do have enough memory to store more than 2 samples in order to make a single comparison, and we do need enough memory to keep track on the global collision counter, but this is very cheap. Okay, so this kind of sums it up. So let's just have a quick look at the simultaneous model and how we can apply our generic recipe to that model. So the constraint of the model, without going far into the details, is that we have k players, but they cannot interact. So each of them can obtain samples and they send a short message to the referee. They cannot interact with one another. And this means that the comparison graph, while representing the entire set of samples through the entire system, actually composed of k-disjoint subgraphs, where each subgraph represents the samples and the comparisons being made by a specific player. And it might not be very surprising that a union of disjoint clicks is the right graph to obtain optimal result for this model. But come to think of it again, it might be a bit surprising that it is the same graph that gives optimal result for this model as well as the streaming model, even though the constraints are very different. So let's just sum up the entire talk. we generalized the notion of collision-based testers or collision-based testing using the definition of comparison graph, where the graph edges basically dictate which comparisons to make. And we gave a generic recipe for uniformity testing that works in various models. And the idea is basically to try and translate all the constraints of the model and the constraints of the tester to graph notations and try to understand which is the correct comparison graph that fits all the conditions that we must hold. And we saw how to apply this to the streaming model and a little bit the taste of how we should apply it to the simultaneous model. And hopefully this might help devising uniformity testers in future models wherever this problem might arise as interesting. So thank you guys and stay safe.